Hi, in this lecture, we're going to cover 4 items: paging, growing stack, memory of the file, and accessing the user memory. The first part is swapping. Here, we basically need to 3 things. First, we need to implement the data structure to represent a physical page frame. And we are required to implement page replacement policy such as RRU, clock, or second chance. And then we need to implement a swapping mechanism which stores the victim page to the swap space and then which loads the required data or page from the swap space or from the file, which is called demand paging. To implement a virtual memory, we need a hardware support from the MMU. There are 2 bits we need to be paid attention to. First one, dirty bit, and second one, access bit. The priority bit of the page table entry is set to 1 by hardware when writing to the memory space. The access bit in the page table is set to 1 by hardware each time the page is referenced. When a page with dirty bit 1 is selected as victim, the updated page has to be stored on the disk. Hardware does not reset the access bit. It means that operating system has to be responsible for resetting the access bit. This is the page table manipulation functions provided by Pintos. It is stored in userprog/pagedir.c. First one is the page dir is dirty. It returns dirty bit of a page table entry for a given virtual page. Another one is page dir set dirty. This function sets the dirty bit to dirty in the page table entry for a given virtual page. Another function is page dir underbar is accessed. As the name suggests, it returns the access bit of page table entry. And the last one is page dir underbar set underbar accessed. As the name suggests, it sets the access bit to accessed in the page table entry for a given virtual page. The first very important data structure, struct page. So you need to define a new data structure. Think about the scenario. We need to select the physical page frame for replacement. We may have to store the page in a given physical page frame and then bring the demanded page to a given page frame. Then what the operating system has to do is it has to select the physical page frame for replacement. So we need a data structure for each physical page frame, which we call struct page. So current Pintos does not have any data structure for a given physical page frame. Now we are defining it. So this is a data structure representing each physical page that contains a user page. This is a very important part because if a physical page frame is empty, then it does not have the associated struct page. So the physical page frame that contains a user page or that contains a valid data has a struct page. The contents is as follows. First, it includes the physical address of a page, which is physical page frame number, and the associated virtual page object. So it is possible that a certain page can be mapped to a different virtual address spaces, such as mmap. And third one is reference to the thread structure to which it belongs. And third one is LRU, field for the list. So as a first step of doing this project, you need to write a data structure. Let's name it as a struct page. And you fill this structure as the attributes we have listed below. And then this is the usage of the struct page in Pintos operating system. This is going to be usage. So Pintos operating system is going to maintain a set of struct pages. Here, we have named it as RU and the build list. It's a global variable. And in this representation, we maintain a set of struct page as a doubly linked list. In reality, you can use whatever data structure you would like to have. For example, you can use hash table or doubly linked list, or you can use some sort of search structure to expedite the search process, such as radix tree or redlect tree. It's totally up to the writer, operating system writer, which data structure it is going to use to represent a set of physical page frame. Anyway, let's look at the details. So there are a global variable RU list, and then there is a bunch of physical page frames which have legitimate virtual page. For example, it has the first field. As a first field, it contains a pointer to the thread structure to which it belongs. And then it contains a pointer to the virtual memory entry, which we have defined in the previous class. And then we needed some other fields. Okay, so the VME field, this is pointer to the virtual entry, points to the virtual entry object. And also the thread field points to the thread structure we have defined. Let me explain this process of swapping out a physical page. First, we have to select the victim page from the list of physical page frames, which is list of struct pages. And then, second, after selecting a victim, we have to check whether a page is dirty or not. If the page is dirty, then we have to write it to the disk. When writing to the disk, the operating system has to select the location on the disk where the given page has to go into. If it's an anonymous page, then given page will go to the swap space. If it's a page from the memory map file, then it'll go to the file. And then it goes to the disk. And then because the associated physical page frame has been released, so we have to nullify the entry. Okay. So that's the process of swapping out a physical page. We have to manage a swap partition. Swap partition resides on the disk, as a part of the disk, but it acts as a memory. So in Pintos, swap partition is managed per swap slot unit, and it is 4 kilobyte. To maintain a swap partition, operating system maintains a data structure, which we call a swap bitmap. This is a global variable in memory. This swap bitmap is used to search the bitmap for the free slots. What happens to a swap bitmap if the system crashes? This is important question. So if the system crashes, all the data structure that resides in memory will disappear. So the swap bitmap is also going to go away. And then it means that we won't be able to identify which one is free and which one is filled in the swap partition. So this is a swap bitmap in memory. And when we are looking for a set of small swap space to store the given victim page frame, we search this list using first fit. So here, the first page is free, and the next 4 page is filled, and then free, and filled, and free. So actual disk partition look like this. There's first page is free, and there are 4 used pages, and then there's free slots, used, and free. Let me explain the functions offered by Pintos for swap space manipulation. Swap partition is a separate lock device in Pintos. There are 4 block device, 4 types of block device in Pintos. And first function is get a block device of a given role. There are 4 roles: OS partition, and regular file system, credit partition, and swap partition. And the function block underbar get underbar role takes the block type as its argument and returns a pointer to the associated block device. Second one is block underbar read. It has 3 parameters: pointer to the block device, then address in the block device, and the pointer to the memory. So it reads the contents of the sector on the block and save them at buffer. The other one is block underbar write. So it has 3 parameters as in the case of block underbar read. First one is pointer to the block device. Second one is the address within the block device. And third one is pointer to the memory. It writes the contents at the buffer at the sector on the block. So we have to implement the followings. First one, we need to implement a LRU list of the physical frame. Well, for the LRU list is just a list. And when you define a function to insert and remove a struct page from the list, you can actually impose an LRU characteristics on a given list. So LRU list is a list of struct page. So it is a list of physical pages allocated to the user processes. And we have to implement a function for allocating and releasing physical page frame from the list. When there runs out of the physical page frame, we have to select a victim and swap it out. And finally, this is the tricky part. Here, the third one is we have to modify the page fault handler for swapping. So before this project, physical page allocate directly when page fault occurs. And if there is no more page to allocate, the operating system just finishes. But now we are using demand paging with swapping. So a physical page is allocated from LLU list when page fault occurs. When there is no more free frames to allocate, then Pintos selects a victim, swap those page to the disk, and bring the demanded page to bring in the demanded page. So this is big change for Pintos, and you are required to implement this feature into the Pintos operating system. These are the functions to write. So function about LLU list, you need a function to initialize, remove, and insert. And we need a function to allocate a page from LLU list, and we need a function to free page from the LLU list. And then based upon these 2 functions, you are required to write a function to select the victim page and swap out the page. So it's a clock algorithm or second chance algorithm, whatever algorithm you would like to implement, you can just plug in those algorithms to the victim selection and swap out process. And then you need to write actual function that does swapping, which means that here swapping means swap in the required data page and swap out the existing dirty page. So these are the functions you are required to write. There are 3 major functions to modify. First one is handle fault. We need to modify the handle fault to allocate physical page frame. If we used LLU mechanism to select the victim, then we have to select it from the LLU list when page fault occurs. And then after allocating a physical page frame, we need to modify the swapping function of the page handle fault. If the page type entry is VM anon, then we have to swap in the page. And then we'll modify the setup stack. We'll see in detail how we have to modify the stack. And then when in the booting, when system starts, we have to initialize the LLU list of the physical page frames. we design a function for allocating and freeing a physical page. We need to try to obtain free space when memory cannot be allocated through pallocate page within the page allocation function. So there is page allocation function, and we call a get page function. If it succeeds, then we are allocated a physical frame, and we add it to the LL list and returns. But it fails, then we need to determine the victim page and swap out the victim page and make the page frame free, and then try the pallocate page again. And this is the steps of freeing the physical page. So it finds the page in the LL list and then delete it from the LL list, and then it calls palloc free page, and then it frees the page. There are functions to modify. All the functions allocate page for user should be modified. When we swap out a page, we have to take different actions based upon the type of a page frame. There are 3 types of page frame: VM binary, VM file, and VM anonymous. When we swap out a page associated with VM bin, if the dirty bit is 1, then we have to write to the swap partition and free the page frame. And when you do that, we have to change the type to VM anonymous for demand paging. When you swap out the file associated with a memory bit file, then we have to take different actions based upon the dirty bits. If the dirty bit is 1, then write the page to the file and free the page frame. If dirty bit is 0, then we can simply free the page frame because the contents of the page frame has not been changed since it has been loaded. The third one is VM anon. For anonymous page, we write the page to the subpartition. And we have to mark the page not present in page directory. So we have to use the function page directory underbar clear underbar page. So this is the control flow of demand paging for swapping out the anonymous page and bringing this anonymous page. When page fault occurs, check whether we have to allocate a page or not. If we have to allocate a page, then we have to check the type of the page we have to bring in. If it's binary file, then load the data from the disk. And if it's anonymous page, then we have to swap the associated page from the swap space. That's 2 things so far. We have to modify the handle fault function as follows. If the virtual page type is anonymous, then we have to modify the code to swap in as follows. So in case of page underbar fault, we take different actions based upon the type of the virtual page. If it's binary, then we load the binary file, and then it breaks. If it's anonymous page, then we have to we have to find the associated page from the swap space, and we have to bring that in. So you have to add the code to bring in the appropriate code from the swap space. Next thing we have to handle is growing the stack. In original Pintos, stack size is fixed. So if the program or user program allocates more local variables than a stack can handle, then it kills the process and then operating system helps. Now we are going to implement expandable stack. In current Pintos, stack size is fixed to 4 kilobytes. So we're going to make the stack expandable. If a process accesses the address that lies outside the stack, and that can be handled by the expanded stack and expand the stack. So example is the address access. If the user application accesses the address beyond the stack, but within the stack pointer -32 range, then we're going to expand the stack. And we will limit the size of the stack for a process as 8 megabyte. We'd like to explain the condition on when to expand the stack. Expand the stack when the memory access is within 32 bytes of the stack top. push a instruction in x86 architecture pushes 32 bytes at once. So for legitimate stack access, if the application generates a stack access within the 32 byte of the stack top, then operating system can consider it as a legitimate and legal access. Let's see that this is stack start 0xC00, and then this is, let's assume that this is the current stack top, which is represented by ESP register. And if an application accesses somewhere between this range, this is 32 byte, then operating system considers it as a legal stack access. But if an application accesses somewhere beyond this range, which is unallocated stack address, then operating system considered it as an illegal access and generates segmentation fault. So this is the extension mechanism of the stack. So this is page fault function, and we need to allocate the page. And then when we allocate the page, we have to check the VM entry type. If it's binary file, then it loads the data from file to memory. And if it's anonymous, then it brings the page in from the swap space. And if it is struct route, then we have to expand the stack. The next topic is memory mapped file. Let's look at the code. We're going to explain the memory map and memory unmap, which is represented by a function called mmap and munmap. Look at this function. There's main function and there's for loop, and we are assigning a certain hexadecimal value to the pointer. And then we open a file, and then we course mmap and file descriptor and data. The format of mmap is as follows. The first parameter is file descriptor. The second parameter is location within the virtual address space where the application wants to bind a given file. So in this case, let's go to the next page. The role of mmap is there is a disk and there's file, and this is process address space, and we like to map a file to a virtual address region. Then what's going to happen is if you store something in this memory address space, then that will be reflected directly to the file contents. So this is more detailed description on mmap function. The first parameter is file descriptor, and the second parameter is the address in the virtual address space where the application wants to bind the file to. So this is the address. So if you call this function, then this file is loaded into this region with this region. So let me explain the details of operating system service for mmap. If mmap function is called, first it creates a VM entry for the individual pages. Here we are. The file size is 3 pages. Let's assume that. And then to map the file to the virtual address space, it allocates consecutive address space that consists of 3 pages. There is 3 pages. So as a first step, the operating system allocates 3 virtual memory entries for each pages for mmap. And then it inserts those VM entry into the set of virtual pages for a process. Remember that we have used hash table to represent the set of virtual pages for a process. So it insert those pages in the virtual page pool. Okay. And then third, as a program accesses this memory region, the operating system is going to bring in the right pages based on demand paging policy. Let me explain the details of mmap and munmap function. First one is mmap. Mmap function takes two parameters. First one is file descriptor, and second one is the address of the buffer address space. It loads the file data into the memory by demand paging. Demand paging means that in mmap, whenever there is a page fault occurs, it loads the associated data blocks from the disk to memory. Memory map page, when the memory map page is swapped out, it is swapped out to its original location in the file, not to the subspace. And it is possible that file size is not multiples of the page size. For example, file size is 10 kilobytes. This is 10 kilobyte. And then we need 3 pages, first page, and second page, and third page. And then in mmap, the mapping has been done in the unit, in the granularity of page. So the last page is fragmented. In that case, the mmap function has to fill the unused fraction of the page with 0. And the mmap function returns mapping ID. So every mapping has unique ID. And mmap fails if the file size is 0, and if the address is not page aligned, and if the address is already in use, or address is 0. And important things, stand.input and stand.output file is not mappable. And munmap function does the other way around. It unmaps the function, unmaps mappings in the map list, which has not been previously unmapped. Following are the requirements when you're writing mmap and munmap. All mappings of a process are implicitly unmapped when the process exits. When a mapping is unmapped, the pages are right back to the file. Upon munmap, the pages are removed from the process virtual page list. And once created, the mapping is valid until it is unmapped regardless if the file is closed or deleted. So this is very important constraints. If the 2 or more processes map the same file, they don't have to see the consistent view. So this is also very important. These are the additional data structures in implementing mmap and additional functions to modify. The first one is a struct mmap file. This is a data structure containing an information from the mapped files. So it contains mapping ID, and it has a pointer to the mapping file object, and then it is mmap file list element, and it contains a VM entry list that is associated for a given mapping. And then we have to modify the handle mm fault. So when page fault occurs, it checks the virtual memory entry type, and then if it loads the data if VM and the entry is file. And also you have to modify the process exit. When exiting a process, it needs to release all the VM entry corresponding to the mapping list at the end of the process. So you have to add a new field called mmap list. This is a set of memory mapped object associated with a thread. So this is, and in this figure, this is a data structure you need to add in existing Pintos operating system implementation. You introduce the list of memory mapped object as a set, and each memory mapped file maintains a list which represents a VM entries for a given memory mapping. Okay. So in this figure, there are 2 memory map files associated with the thread. This is first one and the second one. And first memory map file maps 2 pages. So the file consists of 2 pages. First page and second page. And second memory mapping consists of single page because a file is just single page large. Okay, so this is the final form of the page fault handler for mmap. So this is complete form of page fault. it uh, it implements page fault handling feature for every type of page type. So binary page, file page, anonymous page, and stack growth. So you have now, if you implement all these features, then you are done with implementing the virtual memory. Remember that page fault should not occur in the kernel code. This is why. Let's consider this scenario. There are user context, and there's kernel context, and there is another interrupt handler context. So as the user card makes system core, the context changes from the user to kernel and the kernel to interrupt handler. Let's consider this scenario. First, the user makes a read system core. So read system core consists of read and file descriptor and buffer. Of course, sorry, there is size. Then what the read system core does is there is memory and there is a certain buffer. And then there is a disk and there is a file. And if as a result of servicing you read system core, it reads a certain section of a file into the memory addressed by the buffer. This is basic skeleton structure of servicing a read system core. But the life is not that easy. When executing a read system core, the kernel has to establish an exclusive block on the device, and it reads the data from the disk to memory, and memory is the user buffer. And this user buffer will be bind to some of the page frame, physical frame. What if the kernel asks the disk to bring the memory, and then once the kernel brings the memory from the disk to memory, it copies the required memory to the buffer. So the details process of reading the data block from the disk to user memory is as follows. There is disk, and there is kernel region, and this is user buffer. So when we read a data block from the disk to memory, it first reads the disk block from the disk to kernel, and then copies the block from the kernel to the user. So this is process 1, this is process 2. But consider the situation. While we're loading the disk block from the disk to memory, somehow the operating system has swapped out the physical page that is associated to the user buffer. So this is non-existent. If it happens, when the kernel tries to copy the contents read from the disk, it generates page fault, and then it does swap out, and it might have to allocate a new page frame from the free page list. But here's a problem. We already established an exclusive lock on the disk. So when page fault occurs here, if the interrupt handler tries to access the disk and lock the disk to bring the new page, then it generates a deadlock because it tries to acquire a lock that has been already locked by itself. So we have to prevent the page that are being allocated and accessed by the kernel. So this technique is called page pinning. The objective of page pinning is to prevent evicting the pages accessed during the system core. So this is very important. So whenever you access some page during a system core, you have to pin the page before you start a system core. So to enable this feature, you have to define pinning flag for each physical page. So on every system core, find the virtual page and pin the associated physical page. After system core returns, And before the system call handler returns, you have to unpin the page. For once you introduce the pin flag for the physical page, then you have to modify the swapping handler. For the swapping handler, do not select the pin page as a victim.